Hello APC Mechanics students in Unit 4 System of Particles and Linear Momentum, Class 1 4.1 Center of Mass, Part 1. Section 1, the center of mass. So far we have studied the evolution of a system that is modeled by particle-like object. In other words, in Units 1, 2 and 3, the dimensions of the object were not important. Our knowledge will be generalized to a system of particles containing finite or infinite number of particles. Now, a finite number of particles like the billiard balls. Now, infinite number of particles for an extended object like a baseball bat. Now here, if you consider the baseball bat, it can be made up of several particles. Like if you consider only the first baseball bat, which is here, made up of this particle and this particle. So it's made up of infinite number of particles. كيف كنت أنا بمعقول بدون البان إذا هيك file options advanced حالتين يلا ورا Hello APC Mechanics students in Unit 4 System of Particles and Linear Momentum, Class 1 4.1 Center of Mass, Part 1. Section 1, the center of mass. So far we have studied the evolution of a system that is molded by a particle-like object. Previously in Units 1, 2 and 3, the dimensions of the particle or the object itself weren't important. Our knowledge will be generalized to a system of particles containing finite or infinite number of particles. Finite number of particles like the billiard balls. Now it consists of certain number of particles, consider finite number. Infinite number of particles for an extended object like a baseball bat. So if you consider the first baseball bat, it's made up of, you can divide this bat into infinite number of particles. The motion and dynamics of such systems can be replaced by a unique point called the center of mass, COM for short, as if the entire mass is concentrated in it. All forces are applied to it. Now consider three different systems, 1, 2 and 3, having the same mass and subjected to the same external forces. System 1 is a particle-like object submitted to three forces F1, F2, F3. System 2 consisting of finite number of particles applied or subjected to the same forces F1, F2 and 3, and system 3 consisting of infinite number of particles. This extended object can be divided into several points considered as infinite number of particles and submitted to the same identical forces F1, F2 and F3. Now here we're assuming that these three systems, 1, 2 and 3, have the same masses and they are submitted to the same forces. Then we can claim, since for all three systems the mass and the forces are the same, which means according to Newton's second law the acceleration is the same. But about which acceleration we're talking, that's a good question. The acceleration of the center of mass. Now system 1 is straightforward. It consists of one object. Now for systems 2 and 3, we can talk about the acceleration. Now here, this system 2, we have three particles. They can be replaced by the center of mass. Similarly for system 3, if we calculate the acceleration of the center of mass, it would be exactly the same as the system 1. Now let's consider also another example. A rock is thrown up in air with an angle with respect to the horizontal. It's a projectile motion problem. It will follow a parabolic path. Now what about launching an extended object like a baseball bat? It will spin as it flies, and different points will follow a weird spiral path, except for one point, which is the center of mass of the bat. Now the center of mass of the bat would be located somewhere here according to the mass distribution, because this is the part where the mass is concentrated the most. And however, if we study the motion of the center of mass, we will notice that the center of mass will follow a perfect parabolic motion due to the fact that the entire mass is concentrated in this point, we assume, and it's submitted to the same force, which is the pull of gravity. Remark, another concept related to the center of mass which is found in literature is the center of gravity. The center of gravity of a system of masses is the point at which the net force of gravity acting on the system can be assumed to be applied. Now, if we refer to the definitions of the center of mass and the center of gravity, the center of mass is related to the mass, whereas the center of gravity is related to the center in which the gravity can be assumed to be applied. So both, they have different definitions. Generally speaking, the center of mass is different than the center of gravity. One is related to the mass distribution and the other is related to gravity. However, because in most of the cases we will be working in a uniform gravitational field, in this particular case, both points, the center of mass and the center of gravity, will coincide, and we can safely that indeed the center of mass and the center of gravity are the same and they coincide. If we're talking about points in space in which the field is non-uniform, like pretty away from the center of Earth, and the 2 points are separated by a sufficient amount of distance, we will start to see some deviation between the center of mass and the center of gravity, because this is related to the integration process. However, for now, because we're gonna deal near the surface of Earth, let's suppose, then whenever we refer to the center of mass or the center of gravity, they are both perfectly the same. Now, section 2, locating the center of mass for an extended object dictated by symmetry. For a symmetric shape in terms of geometry, the center of mass of an extended object of uniform density is the center itself. Here we're talking about the center related to the geometry. Consider the following symmetric objects of uniform density. So we have 5 objects that are made up of uniform density. The mass distribution at all points is exactly the same, and we're interested in determining the center of mass, and this can be done by the symmetry, which is the center of the object itself. For figure 1, that would be the center of mass. For figure 2, that would be the center of the rectangle. For a triangle, it's determined by the intersection of the medians. The median is the segment which cuts the side in the half connected to one of the angles, corresponding angles. Now for figure 4, the disk would be the center of the disk, and similarly for the ring. For the ring, the case is interesting. Why? Because the center of mass is located outside the material. For the ring, the mass is contained in this region here, between the inner and the outer radius. However, the center of mass would be found at the center of the ring, outside the material itself. Now, section 3, locating the center of mass for finite particle-like objects. Consider a system consisting of a finite number of particles of masses mi. Here in this case we have 3 different masses, m1, m2, m3 and m4, and we're interested in determining the center of mass. The coordinates xi, yi corresponding for the masses can be determined in an xy plane. Then that's our choice for the xy plane. And x1, y1 would be the horizontal and the vertical position of m1. Similarly for m2, m3 and m4. Then the position of the center of mass of the system is determined using the following formula. The horizontal position of the center of mass, Cm, corresponds for the center of mass. It's the summation of xi mi along the index I divided by the summation mi. And similarly for the vertical position, where xcm, ycm are the coordinates of the center of mass, and the expanded form that would be expressed as follows. The numerator would be the sum of x1 m1 plus x2 m2 plus x3 m3 plus x4 m4 divided by the total mass. Now why here we're summing the index I from 1 to 4? Simply because we have 4 objects. And similarly for the vertical position. These formulas are also known as the barycenter formula and understood as the weighted average of the masses. Why weighted average of the masses? Because as if we're doing the average or the mean of the masses with respect to the position. And now for the rest of the video, we're gonna solve some exercises related to what we have explained so far. Exercise 1. 3 objects are located along the x-axis as shown above. The center of mass of the objects is at x is equal to what? Then here we're gonna apply the barycenter formula given by xcm, which is the summation of xi mi divided by summation of mi. Now how many masses here do we have? We have 3 masses. Then that would, the index I would run from 1 to 3. That would be x1 m1 plus x2 m2 plus x3 m3 divided by the total mass, which is m1 plus m2 plus m3. Now the position of the first mass is 0, then 0 multiplied by 3 plus 3 multiplied by 5 plus 5 multiplied by 2 divided by the total mass, which is 3 plus 5 plus 2, and that would be 25 divided by 10, and that would be 2.5. Now what's the unit? Since all of these positions are expressed in meters, then the unit would be meters, and the correct answer would be D. Exercise 2. 3 objects of mass m, double m, triple m are at position 0, 0, 2, 3, 4, 0 respectively as shown above. The center of mass is located at position. Then here we need to find the position of the center of mass, horizontal and vertical position. Then xcm would be the summation of xi mi divided by summation mi. Now we can directly replace the numbers. 0 multiplied by m, 2 multiplied by 2m, and 4 multiplied by 3m, plus 2 multiplied by 2m, plus 4 multiplied by 3m, divided by the total mass that we have, which is given by m plus 2m plus 3m, which is 6m, and that would be 4 plus 12, which is 16m divided by 6m. The masses get cancelled, and that would be 8 divided by 3. Now here we don't have any unit, and the only one with the horizontal position given by 8 over 3 is A. Now let's double check for YCM quickly. That would be 0 multiplied by m, 3 multiplied by 2m, and 0 multiplied by 3m, that would be 0, divided by the total mass, which is 6m, and that would be 6m divided by 6m, which is basically 1, which makes also A to be the correct answer. Now exercise 3. 2 small spheres are at rest on the x-axis of the coordinate system as shown above. Sphere A has a mass m1 located at a position x, d1. Now notice that d1 represents the distance from the origin to the center of mass of the sphere m1. Now here we're assuming that the sphere is of uniform density, which means the center is related to the geometry, which is the center of the sphere. And similarly for the sphere B of mass m2, we're interested in finding the location of the center of mass with respect to the origin. Now here, because we don't have any vertical position, so the center of mass would be located along this x-axis, and that would be xcm. We have 2 objects of masses m1 plus m2. Now the position of the center of mass of the first sphere is given by d1, then d1 multiplied by m1 plus the position of the center of mass of sphere B with respect to the origin, which is d1 plus d2, multiplied by m2, and it happens that you need to do some adjustment to your answer in order to compare it with these choices. And let me do the following calculation. Now let me expand here. Here we're gonna have d1 multiplied by m1 plus d1 multiplied by m2 plus d2 multiplied by m2. Now here we can factor d1 divided by the total mass m1 plus m2. That would be d1 multiplied by m1 plus m2, and let's split the fraction m1 plus m2 plus d2 multiplied by m2 divided by m1 plus m2. Now this cancels with that, and we're left with d1 plus a fractional mass m2 divided by m1 plus m2 multiplied by d2, which makes E to be the correct answer. Exercise 4. In order to model the motion of an extinct ape, scientists measure its hand and arm bones. From shoulder to wrist, the arm bones are 0.6 meters long and their mass is 4.0 kg. From wrist to the tip of the fingers, the hand bones are 0.10 meters long and their mass is 1 kg. Basically everything that has been stated here is being shown in the figure but not to scale. In the model above, each bone is assumed to have uniform density, which means that the center of the arm is located here, the center of mass of the arm is located here, 0.3 meters from the left of mass 4 kg, and the center of the hand is located here with a mass of 1 kg located at 0.6 plus 0.1 meters from the left end. When the arm and hand hang straight down, the distance from the shoulder, so basically that would be the shoulder here, to the center of mass of the arm-hand system is most nearly, and this can be done using the barycenter formula. Now the first position of the arm, now here the arm is replaced by one point particle of position 0.3 multiplied by 4 plus another point particle given here, a distance of 0.6, and that would be here 0.05, then 0.6 multiplied by, so the distance basically would be 0.6 plus 0.05, which is 0.65 meters. That would be 0.65 meters multiplied by 1 divided by the total mass, which is 4 plus 1. Now plugging that on the calculator, we're gonna have a value of 0.37 meters. Why meters? Because all of the positions are given in meters, which makes C to be the correct answer. Exercise 5. 4 identical uniform sheets of aluminum are welded together as shown above. Which of the following points best represent the center of mass of the system? We have 4 sheets given by 1, 2, 3, and 4. Because we're assuming that they are uniform sheets, then the center of mass of the first sheet is given at the center itself. Similarly for 2, similarly for 3, and similarly for 4. Now we have 4 particles given by 1, 2, 3, and 4. First, let's determine the center of mass related to 2, 3, and 4. That would be at the center, which is 3. So all of these 3 particles, 2, 3, and 4, corresponding for the center of masses of the 3 aluminum sheets, would be replaced by a single particle at the center of the box, which is 3. And the difference between this particle and the one at the top, which is that would be more massive. Alright, so the mass of this particle, which is 3, representing the center of mass for these 3 bottom aluminum sheets, is that this is much heavier than the one. Now here the center of mass related to 1 and 3 would be either point A or point B, because it will be lying along the line connecting 1 and 3. Because C is more massive compared than 1, because 3 represents 2, 3 and 4, this means that it will be shifted more toward 3, which makes B to be the correct answer. Exercise 6. A 5 kg sphere is connected to a 10 kg sphere by a rigid rod of negligible mass as shown above. So this rod has no mass. The only two masses in the system are given by A and E. A is 10 kg, E is 5 kg. Which of the 5 latter points best represent the center of mass of the sphere rod combination? If A and B are of the same masses, then the center of mass would be C. If E is heavier than A, it would be shifted to the right, which means D. Because A is heavier than E in terms of mass, then it would be B, which makes B to be the correct answer. Exercise 7. Two spheres of uniform density are located at a distance L apart, as shown in the figure below. The left sphere has a mass m1 and the right sphere has a mass m2. The center of mass of the two spheres is located at the point P, so P represents the center of mass. Which of the following is the correct expression for the distance from the point P to the center of the left sphere? Then we're assuming that this is the origin, and we need to find the coordinates of the point P, which is basically the center of mass. That would be x1, because the origin has been chosen to be the center of the sphere. Then x1 is 0 multiplied by m1 plus L multiplied by m2, in which L represents the distance from our origin to the center of mass of m2, divided by the total mass m1 plus m2. That would be a fractional mass given by m2 divided by m1 plus m2 multiplied by L, which makes D to be the correct answer. Exercise 8. A 5 kg object is propelled from rest. This is important. From rest, which means the initial speed is 0. By a net force that always act in the same direction. The magnitude of F in newtons is given by explicit function of time. We need to find the speed. Now here we don't know the type of motion. The best way to approach the problem is via calculus. No need to use basically the equations related to kinematics given by, for example, v square x is v square x 0 plus 2a delta x cannot be used here, because if the force is function of time, then the acceleration is not constant, and the kinematic equations that we have studied in unit 1 break down. Then we need to approach the problem using calculus, which means that the speed is the integral of acceleration, and we know that the acceleration is given by force divided by inertia, which is the mass. Now the mass assumed to be constant, it can be dragged out, and the force is given by 0.5 multiplied by t dt. Now here we can now integrate. The integral operator cancels with dt, and the linear becomes a quadratic. That would be 1 over m 0.5 t squared divided by 2, and that would be sorry, I forgot the constant. And that would be 0.5 t squared divided by 2m plus c. Now because this is a polynomial function, which means that the constant is the initial speed, and the initial speed is given by 0, so that would be 0. Then that would be the speed as function of time, and we're interested in calculating the speed at 4 seconds. Our inertia is given by 5. So plugging that on the calculator, we're gonna have a value of 4 meter per second, which makes D to be the correct answer. A particle of mass m starts from rest, which means the initial speed is 0. It moves along the positive x-axis under the influence of a single force given by bt, where b is a constant. The velocity of the particle is given by, so here also the force is variable, which means the acceleration is variable. We cannot use the kinematic equations, and this can be approached by calculus adt, which is given by F divided by m. The mass is a constant, can be dragged out. The force is given by bt dt. Okay, this is a linear term, and its integral would be quadratic, 1 over m bt squared divided by 2 plus a constant, because this is a polynomial function. then the constant would be the initial speed, and the initial speed is 0, then that would be bt squared divided by 2m, which makes B to be the correct answer. Exercise 10. The magnitude of a force as a function of time can be represented by the following polynomial function of degree 2. The direction of the force doesn't change. If the force is exerted on an object of mass m, the change in velocity of the object between t is 0 and t is a capital T seconds is given by what? We know that the change in velocity delta v can be expressed as bounded integral from 0 to capital T of a dt. Here, why we're referring to calculus? Because the force is not constant. We cannot use basically the kinematic equations. That would be F divided by m dt. The mass is capital M, can be dragged out, and that would be the integral from 0 to capital T of RT square minus ST plus Z dt, and that would be 1 over m. Now quadratic becomes cubic. Sorry, this should be small t divided by 3 minus st squared divided by 2. Linear becomes quadratic, constant becomes linear, and this is bounded or computed between two different values, 0 and capital T. Now no need to compute the 0 because it's already 0. Here what we're gonna do, we're gonna compute this once at capital T and once at 0, and we're gonna do the difference. So 1 over m. Now we're gonna replace small t by capital T. That would be r capital T cube over 3 minus s capital T squared divided by 2 plus z capital T minus, no need to compute the 0 because it's explicitly depends on time in the numerator. Then now that would be RT cube divided by 3m minus st squared divided by 2m plus zt divided by m, which makes D to be the correct answer. And finally, the following exercise as an exit ticket. A block of mass 3 kg initially at rest, which means the initial speed is 0, is pulled along a frictionless horizontal surface with a force shown as function of time t by the graph above. The speed of the block at t is equal to 2 seconds. Now here the force is variable, so we cannot use the kinematic equations. We need to approach the problem using calculus. So V is the integral of a dt, which is the integral of f divided by m dt. M is a constant, can be dragged out. Now in order to perform this integral, we need to find f as function of time. Now notice that the shape of the curve of f is a straight line passing through the origin. Then it's given by f equals to slope multiplied by t. Now the slope can be determined by considering 2 points. This is the first point, which is the origin, and the second point, which is 1, 2. So 0, 0, 1 seconds, 2 newtons. That would be 2 minus 0 over 1 minus 0, which is 2 newtons per second. So the function, the force F can be written as 2 multiplied by t. Now we can replace this in the integral. That would be 1 over the mass integral of 2 dt. Sorry, here I forgot the t. Now this is a linear. Its integral would be quadratic, which means 1 over m, 2t squared divided by 2, 2 with 2 cancel, plus a constant c. Now because this is a polynomial function, the constant would be the initial speed, which is basically 0, and that would be t squared divided by m. We need to compute the velocity or the speed at t is equal to 2 seconds, which means 2 to the power 2 divided by the mass, which is 3, which makes it 4 over 3 meter per second, and the correct answer in this case would be A. Then thank you for watching, and see you soon in a new one.